right, welcome back to our Chapter 4.4 video lecture series. And we finished the last video talking about publication bias, which refers to the fact that only statistically significant results tend to get published in academic journals or health journals, medicine journals, that kind of thing. And usually the one study that turns out significant gets published, and no one knows about all the insignificant results, statistically insignificant results. And this is known as the file drawer problem. So all those studies, experiments that are done that do not lead to low enough p-values get put away. And the public, the general public, or at least the set of researchers or experts don't see those statistically insignificant results. And this combined with the problem of multiple testing can yield very misleading results. So I want to go through a kind of fake example, not a fake example, but a comic. This is from an XKCD comic book. All right, jelly beans cause acne. All right, it's a really good comic for stats nerds out there. All right, so someone says jelly beans cause cancer. Scientists must investigate. Let's cross that off for Fortnite now instead of Minecraft. Anyway. We found no link between jelly beans and acne. We got a p-value of greater than 0.05. All right, so the scientist says that's done. Oh, I hear it's only a certain color of jelly beans. Okay, so then jump in. We found no link between jelly beans and purple jelly beans and acne. Brown jelly beans, pink, blue, teal, salmon. Those are probably the grossest jelly beans ever. Red, turquoise, magenta, yellow. None of these are statistically significant. This is a different slide. Now we go gray, tan, cyan, green, mauve, orange, peach, black. Whoa! Green jelly beans. Look at this. P-value is less than 0.05. And then what gets published? Just this study. Green jelly beans linked to acne. 95% confidence, only 5% chance of coincidence. Well, these are not technically wrong. What would be better to see in the paper or in the clickbait blog post or whatnot is 1 out of 20 studies links jelly beans to acne. If you have that information, you might say, okay, well, maybe it's not the jelly beans. Maybe it's just they got one bad sample or one random sample of jelly beans and acne. So this little comment kind of exemplifies that publication bias, file drawer effect issue in modern science and research. So just as a kind of summary of all that, whatever alpha you pick, 5%, 10%, 1%, 0.1%, that percentage of all tests that have a true null hypothesis will yield statistically significant results just by chance. And the one that happens to be significant is the one that gets published. If there are many tests done, then often the researchers only have to publish the one that's statistically significant, or often that's the only one they can publish because of that publication bias. I don't want to scare you too much, but that's a little bit terrifying if you think about it. Imagine if you're running a pharmaceutical company and you develop a new drug that, say, fights acne, and you start testing it, and most of the tests say that your drug does not stop acne, maybe even causes acne. It does the opposite of what you want, but either way, your drug does not work. But since you don't have to publish all your results, you can just keep doing multiple samples until, maybe on your 40th sample of 100 people you're testing, you get a statistically significant result, and then that's the one that you publish, and then try to push your drug out there. So this idea can have very important consequences, both to health, government, how government makes policy. Hopefully the government makes policy based on some statistical data, but hopefully it's not one experiment, one study, and that politicians or lawmakers have all the information that they need. So this leads to something called the Reproducibility Crisis. So it was about 10 years ago, a little more than 10 years ago, there's an increasing concern that most current published research findings are false. And I have these links here if you want to click to these papers, these articles. And we can go a little bit deeper into this idea. It's not necessarily true that the findings are false, but maybe they were not, they didn't have as much strong evidence as was necessary. So many researchers believe that if scientists set out to reproduce preclinical work published over the past decade, a majority would fail. This is, in short, the reproducibility crisis. So this idea, if we have all these studies that have been published saying this is statistically significant, eating chocolate reduces cancer, going to bed earlier makes you happy, whatever study's done, many researchers think if you try to reproduce the experiment exactly, with a new sample, you would not get a statistically significant result on the reproduction. And a recent study tried to replicate 100 results. I'm trying to remember how these 100 results were picked. From psychology journals, so looking specifically at psychology. And the idea is these are a little bit easier to replicate than, say, a medicine, a drug experiment or study, because you have to get, there's some ethic issues and you have to get the drug. So most of these were psychology. 97% of the original results, 97 out of 100, were statistically significant, so yielded a low p-value. And when they reproduced them, only 36% of the replicated results were statistically significant. And this caused quite a bit of shockwaves in research communities. And one extreme you could take is we just can't trust scientists at all, which I completely disagree with. It's not that we can't trust scientists and scientific studies. It's that what I and our authors and a lot of researchers say is that all studies should be published, whether they get to statistically significant results or not. And when you study, you need to put in the conditions that we got a p-value of 0.03, but there's still a chance that the null hypothesis is true, even though we're going to reject it because of that type 1 error probability. All right, so what can you do about this? Point number one is those errors are possible. So keeping track, even though if you don't know for sure if you're making a type 1 or type 2 error, knowing what they are and the probability that they happen are important. Know about multiple testing and publication bias. So if there's a big result you're trying to study, you want to try to figure out if there's a study you're reading that says there's a statistically significant result, eating candy every day will make you happier. You might want to say, okay, well, how many tests were done on this? If you could try to figure that out, that maybe possibly weren't published. Is it all hopeless? What can you do? I hope no is the answer. The first thing is be skeptical when a claim is made. One of many tests are made. So make sure to be skeptical. Always try to do your research if it's something important. I know we're in an information overload age, so you don't have time to be skeptical and check every single claim. But if it's a claim that you think is important and you're curious about, be skeptical and look for replication of results. Has the result been checked more than once, whether it's business, economics, health, sports data? This works the same for all these topics. Okay, so one example, I was listening to a podcast a while ago. I have a link to that on here. The idea of this replication or reproducibility of a study in another setting or by another researcher is important. So if you have a study and then another researcher, say another psychologist, if you're looking at a psychology paper, sets up your experiment and gets similar results, then you're starting to gain credibility. You're starting to build a better case. Studies that have been replicated with different conclusions lose credibility. And this idea of replication helps guard against type 1 errors and helps with generalization. So here's an example I was just talking about. In 1999, psychology researchers tried to test stereotype susceptibility. So they conducted an experiment by taking a random sample of Asian American women and splitting them into two groups. So they randomly split them into two groups. I believe the study was done, I think it was Harvard. I have a link here later. I think it was a Harvard study. And both groups were given a math test, the same exact math test in two different rooms. But before the test, one group was made aware of their Asians are good at math stereotype. Someone passed out the test and had a script to read. One of the researchers or research assistants and said, "Oh, you guys are Asian, so we expect you to do well on this test because of the math stereotype." And then the other group was made aware of the female math stereotype. So before giving the test, they passed out the test, and the researcher said something like, females don't do well on math tests, so don't expect to do as well on this test. Something like that, some type of line to try to stoke those two stereotypes. And then the two groups did the test and to see kind of what would happen. So in this experiment, the Asian math stereotype group, so the group that was told that you're good at math because you're Asian, they performed statistically significantly better than the equivalent Asian female group that were told that they're not as good as math because they're female. So the thought was, the stereotype susceptibility is important. It's the same group of people. There's two different groups, but split up randomly, and one group did statistically better. All right, this experiment was then repeated 20 years later. Actually, a couple of years ago. In two different locations, Georgia. Okay, this is Georgia. I think it was Georgia Tech, University of Georgia. I forget, but it was Georgia, not George. And California. I think it was Stanford, actually. So 20 years later, two different psychologists kind of got together, or psychology research groups, and said, let's try to reproduce this experiment and see what happens. So here I've linked to the Hidden Brain podcast, and it's a pretty interesting podcast. I think it's about 30 minutes if you're interested. They go into this replication crisis in this specific example, and then I link to the original paper. And what happened? In California, if I remember correctly, in California, the two groups performed about the same. There's really no difference in the two stereotypes. So one of them kind of did the opposite effect as the original study. This was not statistically significant. Whereas the group in Georgia did perform statistically significant. The Asian math stereotype did do better than the female math. But it wasn't as statistically significant as the original study 20 years earlier. So I like to highlight this because even if you do reproduce, the ideas here might be, society has changed in 20 years, so maybe the stereotypes aren't as strong as they used to be. And then they also did these studies in two different coasts, in two very different parts of the United States. So it could be the case that maybe on the East Coast or the South, these stereotypes, susceptibility still exists. Or maybe in California, this was the most random group that performed the same. It's kind of hard to tell. And this is one of those, I don't think there's a concrete answer with this situation, at least from these three studies done. And that's, I would say, kind of the march of science is you're kind of slowly trying to understand something like a stereotype susceptibility. And in general, for a lot of things, you don't get a completely concrete answer. You just kind of build a case, you build more evidence, and try to see what side you think might be true. All right. Okay, so how can we reduce the probability of making a type 1 error, rejecting a true null hypothesis? If you want to reduce the probability of making a type 1 error, you should decrease significance level. Make alpha as small as possible. How can we reduce the probability of making a type 2 error, not rejecting a false null? In this case, we want to increase the significance level. So the idea is whatever alpha you pick, if it's your p-value is less than alpha, you reject the null, but you could be making a type 1 error if the null is true. And this is your chance of a type 1 error. And anything bigger than alpha, if p-value is bigger than alpha, you do not reject the null. You could be making a type 2 error if the alternative is true. And